Hello students, today in our 12th standard physics, electrostatics is our lesson today, and this is our episode number 12. Students, today we are going to learn about some different at the same time short topics. First one, we are going to see about the dielectrics and insulators. In the dielectric and insulator, we are going to see a subtopic named as polar and non-polar molecules. Let's see about the polarization, then induced electric field inside the dielectric, dielectric strength, capacitors and the capacitance, and finally we are going to see an expression for a capacitance of a parallel plate capacitor. Students, in dielectrics or insulators, you may know many things about these insulators because all our electric connections are insulated, because the electricians will not allow the current to move freely outside the conductors, so they insulate all the materials. Now let's see what do you mean by this dielectrics. A dielectric is a non-conducting material and has no free electrons. The electrons in a dielectric are bound within the atoms. Examples are ebonite, glass, mica, and sometimes we can take paper as a dielectric material. See, these dielectric materials are made up of polar and non-polar molecules. Come, let's see what do you mean by polar molecules and non-polar molecules. First of all, polar molecules. In polar molecules, the centers of the positive and negative charges are separated even in the absence of an external electric field. The polar molecules have a permanent dipole moment, and due to thermal motion, the direction of each dipole moment is oriented randomly. Examples are H2O, N2O, HCl and NH3. Now let's see what you mean by this non-polar molecules. A non-polar molecule is one in which centers of positive and negative charges coincide. As a result, it has no permanent dipole moment. Examples of non-polar molecules are hydrogen H2, oxygen O2, and carbon dioxide CO2, etc. Now let's see about the polarization. What do you mean by polarization? Polarization is defined as the total dipole moment per unit volume of the dielectric. Again I remember for you. Dielectrics are examples glass, mica. Okay. For most dielectrics, that means the linear isotropic, the polarization is directly proportional to the strength of the external electric field, and it can be written as P polarization is equal to XE and E external. Here the external electric field is directly proportional to the polarization. Here Xe is the constant, okay, size is a constant, and they are called as electric susceptibility, which is a characteristics of each dielectric. Let's move to induced electric field inside the dielectric. Again remember, dielectric is another kind of insulator which does not conduct electricity. never allow the charges to move across the surface. Now, when an external electric field is applied on a conductor, the charge is aligned and cancels the external electric field because it never allows the positive or negative charges to move across them. So, it cancels the external electric field. Second point, but in dielectric, the external electric field only realigns the charges so that an internal electric field is produced. The magnitude of the internal electric field is smaller than that of the external electric field. There are some pictures. Okay, they have been, the first one, they have been aligned positive and negative in a uncontrolled manner, but here the positive and negative have been arranged in a controlled manner. Okay, you can separate the positive and you can separate the negative things. The net electric field inside the dielectric is not zero, but is parallel to an external electric field with magnitude which is less than that of the external electric field. The uniform electric field between the plates acts as an external electric field E external. You can see here and here, which polarizes the dielectric pace between the plates. Okay, this is internal and this is external. The positive charges are induced on one side surface and negative charges are induced on other side surface. But inside the dielectric, the net charge is zero. Okay, the net charge is zero even in small volume. So the dielectric in external field is equivalent to two oppositely charged sheets, this positive and negative charge sheets, with the surface charge density plus sigma b or minus sigma b. These charges are called bound charges. They are not free to move like free electrons in conductors. The dielectrics never allow. Okay. Next one, dielectric strength. I already explained you about the dielectric materials and the characteristics of dielectrics. Now, what is the strength of the dielectric? See, if you take a glass as a dielectric material, we should know the strength of that dielectric material. Okay, or if you take a mica sheet, we should know the strength of that mica sheet to retain its dielectric power or strength. So there are some ranges for all the dielectric materials. Example, the dielectric strength of air is 3 into 10 to the power 6 Vm minus 1. When the external electric field is applied to a dielectric is very large, it tears the atom apart so that the bound charges become free charges. Then the dielectric starts to conduct electricity. This is called dielectric breakdown. The maximum electric field the dielectric can withstand before its breakdown is called dielectric strength. This you all know, and if you go through the book, you can see a lot of dielectric strengths about the materials, mica, glass and etc. Paper also. Now let's move to the capacitors and capacitance. Students, let me tell you one thing. The capacitors are used widely in many electronic circuits nowadays and have applications in many areas of science and technology. You can see the capacitors even in all electronic circuits, and even you can see the capacitors in our cell phones, in watches, everything. So what do you mean by this capacitors? Capacitor is a device used to store electric charge and electrical energy. It consists of two conducting objects, usually plates of or separate sheets. They are separated by some distance, and you all know the distance between the dielectric is 2a. Now, what is the capacitance of the capacitor? If you describe a student of class 12, we should know about the capacitance of that students. Then only we can go through the students' strength, because all are not equal. So we have to differentiate the capacitance of the each and every students like this. The capacitance of a capacitor is the charge stored in the capacitor is proportional to the potential difference between the plates. That means plus charged plate and minus charged plate. Now Q is directly proportional to V, or Q is equal to C into V. Here C is the proportionality constant called capacitance, and capacitance C of a capacitor. The capacitance C of a capacitor is defined as the ratio of the magnitude of charge on either of the conductor plates to the potential difference existing between the conductors. The SI unit of capacitance is coulomb per volt or farad F. Capacitors are available in the range of microfarad. 1 mu F is equal to 10 to the power minus 6 F to picofarad. 1 PF is equal to 10 to the power minus 12 F. Let's move to the expression for a capacitance for a parallel plate capacitor. Now consider a capacitor with two parallel plates. See, a capacitor with the two parallel plates, each of cross sectional area A. Both the plates have a cross sectional area A, and they are separated by a distance D. Both of them are separated by a distance D. You can see all these things in the picture. Now the electric field between the finite parallel plates, this finite parallel plates, is E is equal to sigma by epsilon naught, where sigma is the surface charge density on the plates and sigma is equal to Q by A. That means the charge divided by the area, cross sectional area. If the separation distance between them are D is very much smaller than the size of the plate, that means the size of the plate is very much high but the distance is very low, then we can put D square is very much less than A, that means the area. The electric field between the plate is E is equal to Q by A epsilon naught. Okay, this E is equal to Q by A epsilon naught. This is going to be the equation number 1. The electric potential between the plates having a separation D is given by V is equal to ED equal to QD epsilon naught. Actually, not many things. We add a distance D here. So, the QD divided by A epsilon naught. This is the second equation. Since the electric field is uniform, the capacitance of the capacitance given by C is equal to Q by V. That we all know already, because Q is equal to CV. So we take the V here, Q by V, and instead of V we put the term QD divided by A epsilon 0 using the last equation 2. While you cancel this Q and Q, okay, you get A epsilon 0 in the upper side and the D in the bottom. So epsilon naught A divided by D. From equation 3, it is evident that the capacitance is directly proportional to the area of cross section, okay, and is inversely proportional to the distance between the plates, that means that D. Using this, we understood that the area of cross section of the capacitor plate is increased, more charges can be distributed for the same potential difference. As a result, the capacitance is increased. Now, if the distance D between the plate is reduced, that means it has been shrunk, the potential difference between the plate V is equal to ED decreases with the E at constant. Suppose the distance is increased, the capacitor voltage increases and that becomes a greater than the battery voltage. Then the charges flow from the capacitor plate to battery till both voltage becomes equal. These are the important things in the capacitance for a parallel plate capacitor. Thank you students. See you in the next class.